Bismillah ar-Rahman ar-Rahim. So what I'm showing you here is something that we have done earlier, which is related to the calculations of the angle of incidence on a surface. And this surface basically is a fixed surface, which is not moving. And we use this equation, which is, as you see it here, equation 162, the long equation here, where the same equation is rewritten as 163 in terms of the zenith angle cosine theta z. So these two equations are exactly the same. What we did is that we have just substituted in the expression of cosine theta z in the first one, and that resulted in that shorter equation. Or we came to equation 163 and we substituted cosine theta z and sine theta z in the equation, so it resulted in this extended one. As I mentioned earlier, we do not memorize these equations. They will be provided to you, especially that, as you probably remember from our last class, we have seen many special cases. And I just brought this equation so that we remember that all the special cases are coming or are extracted from this expression here. You just apply the condition and then you try to algebraically manipulate the equation so that you reach for a shorter expression for the angle of incidence. To show you we were considering last time also the case where the surface is not fixed the whole day, but it is tracking the sun, which means that it can be moving with time so that it can attract or it can absorb as much as possible from the solar energy because of the motion of the sun in the sky relative to an observer standing on the ground on the earth. Accordingly, this can be done with several positions. For example, we can fix the angle of rotation, a single axis, that would be placed in the east-west direction. So the whole surface or the collector, let it be a PV panel, or it can be a solar thermal collector, whether it is a flat plate or a parabolic trough or even a paraboloid. These are the different famous types of solar collectors that are being used. And these solar collectors would be rotating about one axis. The axis that I mean here is basically an axis which is in the east-west direction. In this condition, the cosine theta reduces to that form that you see here by equation 171. Sine squared delta, the declination angle, plus cosine squared delta cosine omega, and omega is the hour angle, where beta, which is the declination angle, can be given by phi minus delta. The surface azimuth angle for this case, because it is fixed or the axis is in the east-west direction, so the azimuth angle is going to be either 0 or 80, depending on the latitude, whether it is facing south or facing north. Now, that was if you are going to track it, and the tracking here is done on a daily basis. You just adjust it according to a certain scheme. What if you are doing a continuous adjustment to minimize the angle of incidence? In this case, cosine theta is given by that expression here. And then the beta and gamma are accordingly calculated according to these equations, 172, B and C. So when we are talking about a horizontal east-west axis, then we have two conditions. One of them is this one, where we'll do some sort of a single daily adjustment. Whereas the other one is going to be having a continuous adjustment. And how do you know that if you are solving a problem? This has to be mentioned to you explicitly. So we're going to tell you that this condition applies to a surface, or are going to deal with a surface which is having a single adjustment, or a surface that has continuous adjustment throughout the day. Now, the other conditions here would be, what if the axis is rotating about a north-south axis. So you are putting your axis as a north-south horizontal axis, and the rotation then becomes going from east to west. Under this condition, the angle of incidence is calculated as cosine square theta z. Theta z is the zenith angle, plus cosine square delta sine square omega, all square root. The slope, again tan beta, is given by this equation, tan the zenith angle into cosine the azimuth angle minus the azimuth orientation of the plate. So the solar azimuth is gamma s, and the azimuth angle of your plane is gamma. And then the gamma is being calculated here. So again, we are talking about an axis in the north-south direction with continuous adjustment. If you go back to the book, you'll find that it's probably giving you what if we have a north-south axis with a single adjustment, it will give you another set of equations. If you probably noticed here that we are moving in sequence here, and each one of them is having a set of equations A, B, C. A is the angle of incidence, B is the tilt angle, and C is the gamma, which is the azimuth angle. What if it's a vertical axis? In case of rotating around the vertical axis, then the cosine theta, or the angle of incidence, is cosine theta z cosine beta plus sine theta z sine beta, where beta is constant because we said it's a vertical axis. And gamma is equal to gamma s, and these are additional expressions in case we have continuously tracking or continuously tracking surface which is being adjusted. So as I mentioned here, for each problem that you are going to be exposed to, you should be told exactly what is the case that you have in hand. Normally, I would, if I'm solving a problem like this, I would probably consider the case that why should I memorize all of this? I can just get the general equation that I've showed here today at the first one and use it. But these are, I mean, some additional equations that are given to make your life easier when you are going to solve problems like this. Let's look at this example. Calculate the angle of incidence of beam radiation. The slope of the surface and the surface azimuth angle for a surface are given here, and the values are given. Phi, latitude angle is 40, delta, declination angle is provided to us, omega, the hour angle is 30 degrees. This all is at 2 p.m., whereas another condition here is for beta is equal to 40, phi is equal to 40, delta is 21, omega is 100. So it's the same value of the phi, it's the same value of delta, but it's at different hours. So that's why the hour angle is different. And the condition is being given here that it's actually underlined, continuously rotated about an east-west axis to minimize theta. So I'm going to look at the equations that are available, and I'm going to select the equation that represents the case of continuously rotated surface about an east-west axis. And then I'm going to use the equations which are associated with this, which are these equations. Or basically, it's the first equation that we have here, which is theta, the angle of incidence, is inverse cosine of 1 minus cosine square. The 21 here is delta. Sine square 30 here is supposed to be the value of omega. And then you can determine the angle of incidence. The zenith angle, it has a fixed definition, as you can see it here, which is basically cosine phi, cosine delta, cosine omega, plus sine phi, sine delta. Then you can get the value of the zenith angle. Gamma S can be calculated, and this is the definition, if you remember, for gamma S, as we did last time, and we had an example on, and that's the value of beta. So what is different here in this expression is that, or in this example, is that because it's a surface which is continuously rotated about an east-west axis, we have used this equation of theta, which is associated with that. The other equations are standard, are the ones that we have seen earlier. Now, The part B of the example is if everything is the same as you can see it here, but the value of omega is different. And this is what we do here. We have just calculated or substituted for omega is equal to 100, from which we can get the values of theta, theta z, and gamma s, as well as beta. So the point here in these examples is it is showing you then how you can use different expressions of the angle of incidence depending on the nature of the surface that you are dealing with. Now, for design and performance applications of solar process, as we will see it later, some sort of a standard procedure which is being followed is to calculate the hourly radiation on a tilted surface as related to or with respect to the radiation on a horizontal surface. So it's a ratio that we are looking for. And this ratio basically is related to these two values, cosine theta, which is the cosine of the angle of incidence, and cosine theta z, which is cosine of the zenith angle. And both are shown to you here. So cosine theta and cosine theta z. Cosine theta or theta basically is this angle here, and theta z, as we have seen the definition, is this angle. Now, this is the angle between the incident radiation and the normal radiation to the surface. This is the incident angle of incidence, and theta z is the zenith angle, which is the angle between the ray coming, or the normal ray coming from the sun, and the zenith direction, which is vertically upward. The ratio that we are looking for, which is basically the radiation incidence on a tilted surface to the radiation normal, which is basically given by an expression or a symbol that we refer to as R sub B. This ratio of R sub B is basically the irradiation falling on a tilted surface divided by the irradiation on normal surface, and on normal surface. And you can see it here. The value is given as basically cosine theta over cosine theta z. Then probably you would anticipate, or you can expect now, that we are going to consider examples of calculating RB based on different cases. The general case, and which is we're having a fixed surface or a fixed collector, or the case in which we are tracking the sun, and the tracking can be on an east-west axis or around a north-south axis, or tracking parallel to the Earth axis of inclination, or a vertical one, and each one of them is going to have the values of cosine theta that we have seen the different equations for are going to be represented here. Whereas the cosine theta z, that's a fixed expression. So cosine theta can take any one of the equations that we have considered previously and we have taken an example for, based on the condition that we have. Is a fixed location, or rotating with a single adjustment, or continuous adjustment on the four cases that we have considered. One of them is rotating around an axis in east-west direction, around an axis in the north-south direction, around an axis which is parallel to the axis of inclination of the Earth, or around a vertical axis. And that is what you can see here in front of you. This is the general case. You are talking about asking for the ratio of the beam radiation to that on a horizontal surface for a surface and time specified in example 161. In example 161, it was a fixed surface which is not rotating at all. A flat plate collector, for example, that you are putting into a certain direction and the direction does not change. And this is why you can see the long equation here for theta. That's the one that we have seen earlier and the one that I started with today. So cosine theta can be calculated from here. And to remind you of example 161, here are the values. It's talking about 13th of February, so n is equal to 44. Delta has been calculated as minus 14, depending on that day. Remember, delta is a function of the day. Omega is minus 22.5. I would recall that this probably was 10:30 in the morning solar time. Gamma is equal to 15. Beta, it is tilted 45 degrees centigrade, and it was in Wisconsin-Madison with an angle of latitude of 43 degrees north. So for these conditions, they can be taken and substituted here in the expression of cosine theta, out of which theta has been calculated as equal to 35. Angle of incidence we calculated in example 161. If you go back to the first presentation, you will find that example, and the value of theta has been calculated there to be 35. For a horizontal surface, the standard definition of theta z, or cosine the zenith angle, is given by that. And then cosine the zenith angle is given as 0.491. Now, what we are looking for here is the ratio of the beam radiation to that on horizontal surface. Cosine theta, 0.818, divided by cosine theta z, which is 0.491, so the ratio is 1.67. So the example was basically looking for this value of the ratio, normal beam radiation to the horizontal one. The optimum azimuth angle for flat plate collector is usually 0. If you have a flat plate collector which is not moving, what you would do basically is to orient it toward the south so that the gamma angle or the azimuth angle is equal to 0. If you are in the lower part of the atmosphere of the Earth, for example, if you are sitting in Australia, then you are going to make it facing north. If you are sitting here in Saudi Arabia, you'll make it facing south. And that's why basically basically when we are doing any solar collectors, whenever you have an opportunity to visit the university, you will see that we have some solar collectors who are placing outside building 26, and some of our experimental work with solar desalination systems, you'll find that we are orienting our solar collectors so that they can face south. If you happen to visit the beach, the KFUPM beach, and go into your bachelor section of the beach, before you reach to the circle that leads to the different units that you have there in the beach, you'll find to the left that there is a certain location that has a fence and a couple of gates, and it has solar collectors in. They are basically, again, that belongs to our research area where we are doing experiments on desalination systems using solar energy. You'll find that there we have a PV system for electric generation, and we have evacuated tube collectors and a flat plate collector, and all of them are facing due south. So what we do, we check what is the south direction, and we make all our unit facing south. So the value of gamma there is going to be equal to 0. In this case, the equations that we have used earlier for determination of RB can take these values. And remember for these expressions that the denominator is basically cosine theta z. So this is cosine theta z here, and this is cosine theta z here. What is difference here is the numerator that would change. So in this case, the equations that we have considered before, cosine theta z is given, and cosine theta is the one which is given that expressions that we have here. And this is for the first one here is for the northern atmosphere, and the other one is for the southern part or northern part of the hemisphere of the Earth, and lower one is the southern part of the hemisphere. And remember that here we are talking about cases where gamma is equal to 0. So if you are going to take that long expression of cosine theta and substitute gamma equal to 0, you would expect, I mean, with algebraic manipulation, you can get that value in the numerator here. Again, all of these equations are going to be provided to you. The point is you should know which equation to use based on the problem that you have in hand. Another special case, if you are talking about in the interest of RB at noon, then the ratio can be given here for the northern hemisphere and for the southern hemisphere as well. As probably I mentioned it last time, and that engineers tend, or probably that was something in the few decades ago, they prefer to use charts so that you spend quite a bit of time. And we have seen the chart of earlier last time where we can use it to determine what is the sunset hour and what is the period of or the number of hours between sunrise and sunset. And that can be given by a diagram. We've looked at the diagram last time, and we said that diagrams or the graphical representation, it's too easy to use it for determination of the values that you want. But the accuracy is going to be less if you compare that with the equations. Currently, there are softwares that are doing that. So now you have the freedom to have to use three types of or three ways to get your calculations done, either or to get the values that you are looking for in terms of either angles or ratios. You would either go to the equations that we write here, and this is the accurate ones that you can do it yourself by your hand using a calculator. Or you can use figures to determine these values, which are much easier, but on the other hand, it is on the expense of accuracy. Or you can refer to some of the softwares that are available, or maybe make your own software, write a little program on Excel, like the example I've showed last time, or you can write it engineering equation solver if you have access to it, and then you can have a program that does the calculations to you. All you have to do is insert the conditions that you have. If you are good at MATLAB, you can do it through MATLAB, and then you just enter the angles that are determining the latitude angle. For example, what is the azimuth angle, what and so on, and then you can calculate whatever values that you want. Orientations like what is the azimuthal angle and what's the value of delta depending on the day of the year and so on, the tilt angle. And then you put all of these in your program, and then you don't have to recalculate every time. You just put your data and you'll get your results out. Here we are talking about a set of graphs which are located in the book. They are basically 1, 8, 2, figure A, B, C, D, E. So 5 figures are given so that they can provide us with cosine theta z and cosine theta as well, depending on the values of phi, the latitude angle. So knowing the value of phi, you can get cosine theta z, and knowing the values of phi minus beta, you can determine the value of cosine theta. So this can be given right away by just using these figures. Examples are given here. So this is an example where the x-axis, as you can see it here, it represents either the latitude phi or phi minus beta. So I can use the x-axis for either one of them, depending on what is it that you want to calculate. For example, I can use this phi if I want to calculate cosine theta z. So this one is corresponding to that. And I can use the value of phi minus beta if I want to calculate the value of cosine theta. What we have here is these angles extending from 0 to 60. And here we have different lines. Each one of these lines is representing a certain date, for example, and it's selected day of every month is here. So December 10, January 17, November 14, February, October, March, September, April, August, May, July, June. So if you count them, there will be like 12 figures, and each figure is presenting a month, a day of the month. And if you are in the northern latitude, you are going to consider this column to the left. If you are in the southern latitude, like in Australia, for example, then, or South Africa, then you would consider this. So depending on your location, are you in the northern part of the hemisphere, northern hemisphere of the Earth, or the southern part, and then you can pick your value. We are going to take an example on that. And the figure that you can see here in front of you applies only for the hours between 11 to 12 and 12 to 1. For surfaces that are tilted toward the equator, which is natural. And that's one figure. There are 5 figures, and each figure is different in terms of the angle of the hour that it represents. So this is 11 to 10, 10 to 1. This one is from 10 to 11 and from 1 to 2. And then you are going to have different figures from 9 to 10 and so on. So these figures would represent a tool for calculating both cosine theta z and cosine theta, so that if you are looking at the ratio RB, then you will get the values of cosine theta z, and the ratio RB becomes cosine theta divided by cosine theta z, and here is it. So here, you don't have to use any equations. You can just pick up the values from here. But as you can see here, the kind of accuracy is not going to be exactly what you are looking for. You're going to have another problem if you have a different day. For example, if I'm looking uh, for example, December 30. Wow, this is December 10 and this is January 17. So I have to visually come approximately somewhere in the middle and pick up the value. Here, the issue of accuracy becomes a little bit tricky. You are 18, and probably if you are solving a problem with a date of December 20, then I would expect 18 different answers. None of them is wrong, but all of them are approximately correct. So it's hourly basis, and we would be able to calculate the values of theta and theta z, and from which we can calculate the value of RB. The values are more correct toward the middle of the day, but the accuracy is less and less if we are talking about sunrise and sunset. So there's also a limitation in the utilization of these figures. So how to use it? Let's pick up an example, and actually a couple of examples, because of one reason. The reason is sometimes when you are going to solve for the values of, or you are going to consider the values of theta minus b, or the values of phi minus b. Again, phi, what is phi? It's the latitude angle. What is beta? It is the tilt angle. Sometimes beta is higher than phi, so the value here becomes negative. If the value is negative, you are going to take it as a positive value, but you are going to look at the other column here. So the dates are going to be corresponding to the other column, and this is the recommended way to use it. So if you have phi minus beta is positive, you are going to refer to the values in the north latitude. If you have phi minus beta is negative, then you are going to pick up the values corresponding to the south latitude. Now, we do that because we are sitting in the north. If somebody is sitting in Argentina or somewhere in Australia or South Africa, is going to reverse it. We don't have to confuse with this. So the point is, as long as phi minus beta is positive, we're going to pick up the values corresponding to the north latitude. If phi minus beta is negative, then we are going to pick the values corresponding, or the dates corresponding to the south latitude. So this is all that you need to know about this figure, and knowing that the accuracy is weak if we get to the ends of the day, either end, sunrise or sunset. Let's pick a couple of examples that are considering this so that we can test each one of them. Use figure 182. See, he has specified the figure. He doesn't have to. He could have just given the hour and that would be enough. But anyway, it is given here just for confirmation. Calculate RB for a surface at latitude 40 degrees north, a tilt of 30 degrees. So phi is 40, beta is 30, phi minus beta is plus 10, toward the south for an hour 9 to 10 solar time on February 16. So what you do here, number one, look at the hour so that you can pick up the figure. If you remember, figure A was handling between 11, 12, 12 to 1. Figure B, 10 to 11 and 1 to 2. Figure C, it is basically 9 to 10 and then 2 to 3. So we should be going for figure C then. February 16 is the day, is the line that we're going to select from the figure to get the value. And what we need here is a couple of things. We need the value of cosine theta and cosine theta z. The cosine theta z is going to determine on the value of the latitude angle 40. Cosine theta is going to determine on the difference between these two. And this can be calculated either from the figure You can see here from the figure things appear to be easy because all you have to do is just pick a value from the figure here, which is intersection of two lines. Intersection of other two lines, you'll get this value, and then you get the final answer. But if you need to calculate it using the equations, this is what you do. You are going to, we are talking about February 16. So January is 31 plus 16. So N is equal to 47. And for N is equal to 47, you are going to substitute in the expression of delta to get the declination angle as minus 13 and then substitute here in that expression. Then you can get the ratio. And this value is the most accurate, by the way. And you can see here, there's a little less accuracy associated with values that you are going to get from the charts. And as I mentioned, if you are doing that, you are 18, you are going to get different values for each one of these. But all of them will be around this. It will not be too far. Now, this is what we do. We need the value of cosine theta z. Cosine theta z depends on phi. Phi is equal to 40. So I'm going to construct a vertical line at 40. And then I'm going to pick the day. The day they said it's February 16. So this line here. So the vertical line is going to intersect with this line at a point. And this point is corresponding approximately to 0.45. This is 0.4. This is 0.5. So this is almost in the middle. So 0.45, which is cosine theta z. But if we want the value of cosine theta, then we need phi minus beta. Phi is 40, beta is 30, so the difference is 10. So at a value of 10 here, we are going to construct a vertical line. I'm doing it here a little bit aside so that you can see it. If you are solving it yourself, you are going to move into that black line. Vertically, it's going to coincide again with this line of February 16 at a point. This point should be a little bit above. And then you can get the value again, 60, 70, 72, or 73. Now you can get this value. So this is cosine theta. This is cosine theta z. When you substitute here cosine theta over cosine theta z, you get the value of RB, or the ratio that is needed between the normal beam to the horizontal one. Another example, which is given here, it is calculate RB for a latitude of 40 at a tilt angle of 50. Now the tilt angle is higher than the latitude. It is facing south also for the hour 9 to 10. So hour 9 to 10, that's the same figure, figure C that we have. The value of the tilt angle does not affect the zenith angle. So the zenith angle is going to remain the same as we did in the previous calculation, the previous example. What's going to make a difference is the value of phi minus beta here is going to be minus 10. Because it's minus 10, what I have to do, I have to go to the figure here, definitely the value of theta z, as I mentioned, at 40, phi equal to 40, a vertical line with 16th of February, then you get the value of cosine theta z here. The other one, it's minus 10. So what I'm going to do, I'm going to get to that plus 10, and it will go up here and it will intersect with the value of the day, 16 February for the southern atmosphere. 16 February for the southern atmosphere, it is this line. So it should coincide with this line here at a certain value, and the value is close to 0.8. So accordingly, the RB is going to equal to the ratio of 0.8 divided by 0.45, and it's being calculated here as 1.78. If you are going to use the equation and substitute for theta, for phi minus beta is equal to minus 1, here is it, cosine, the difference is minus 10 cosine delta and then cosine omega, and then you can substitute and get the value. More accurately, it will be 1.79. Definitely, when you look at the figure, you can never come up with 3 digits from the figure. That's why from the figure, we just got it as 0.45. Any questions? So the bottom line is you have a couple of tools here that you can use for the calculations. One of them is by using the equations and these equations are going to be provided to you. But because the way that practically engineers preferred figures so that they can have quick calculations, figures are provided and you can use the figures, they are easier to use. However, we have an issue with accuracy of the figures. Here it does not seem to be a big issue. Talking about 0.01 is not a big deal. But as I mentioned, if several persons are looking at it, they can come up with several answers. However, these answers, all of them are approximately correct. These figures that we have, some sort of a cross plot of the figures, they were plotted again so that they would provide us with a cross plot between the value of RB right away as the delta has changed. Delta change, it means that the day has changed. So for several days over the year, you can get the value of RB right away at different angles. So this values of the point 5.5 or 4.5, 3.5, this is basically has to do with the angle, with our angle. Accordingly, for a certain conditions, this is a replot of the previous figure using basically the equations that we have so that you can show the effect of the collector tilt, which is on various times of the year and the day. So that's another way that you can do. But anyway, this has to be for a given latitude and slope. So you are talking about a latitude of 40 and a slope of 50. If you have to change the latitude or the slope, then you need to make another figure like this. So it's probably not practical, but it is just showing one way to represent the same results that we have. You can get RB right away, but for every latitude and for every slope, you have to make a different figure. All of them are originated from the equation. So all of them are obtained by just substituting here. Which means that to generate that figure, what we have done, we have fixed the value of phi, we have fixed the value of beta, and what we have changed is basically a couple of things. Delta for a constant omega, and omega for a constant delta, and then you can get these figures, this figure accordingly. The equations that we have can be used not necessarily for a fixed surface. As I said, remember we said that the general expression that we have taken last time that I started with today was for calculating theta for a fixed surface. However, it doesn't have to be fixed. It can be rotating on a horizontal east-west axis or a horizontal north-south axis or a vertical axis or axis which is parallel to the axis of rotation for the Earth. And for each one of them, what I'm going to change is the numerator. Remember, the numerator is cosine theta. And today we started with a couple of examples in which we have rotation of or continuous rotation of the surface over an east-west axis, where we use that expression here on the top. So this expression on the top in the numerator can be changed based on the condition that you have. It can be the general case with the long equations for cosine theta, or some special cases, whether it is pointing to the south, for example, so that gamma s is equal to 0, which is one of the simplifications that we had, or the case in which it is rotating on either axis, and then the corresponding value of cosine theta can be represented here on the top. One of the problems that we are facing in placing the solar collectors is shading, especially if you have to place your solar collector in an area which is not open. I was talking to you about location of our solar collectors in the beach. Why the beach? Simply because it's a flat, open area. There are no buildings there. There are no trees. Trees and buildings may make a shading of our solar collector. If you have to put a solar collector in our areas here, you would put it on top on the roof of your house. And it would be better if you have a high-rise building, you put it on the top of that high-rise building. Because if you are talking about a building and there is another building which is taller than it, then some shading effect is going to be there. Which means that for some part of the day or some part of the year, you may have your solar collectors being not exposed to the sun partially because the shadow of a tree or shadow of another building is covering part of it. And there are interesting videos in the internet where the calculations are being done. I've just seen a video a couple of days ago where they are putting some solar collector and seeing the effect of changing the tilt angle, and the values are going to be measured by having devices to measure the voltage, the ampere, which is coming from the PV panel. And then the presenter put her hand on the solar collector as to show how the shading effect would be there. And it may have a significant value. I mean, we are talking about sometimes when we are running our experiments on solar desalination systems, you find that the productivity has reduced tremendously for a certain part of the day. And that was basically because there's a cloud that was passing that was hiding the sun. And during this period, there's no sunshine. And then if you are talking about a PV system, then the voltage and the ampere definitely are going to be affected. If you are talking about a solar heating system, you'll find that the heat or the temperature of the fluid that you are heating, be it air or water or oil, the temperature has dropped just because of the shading. So shading is a parameter that can substantially affect the performance, and that's why it's important to determine it. We are not going to cover shading right now in details, but we are going to talk about it in chapter 14 in the book, where probably you can maybe specify some sort of a whole class talking about shading and the shading effect. The three types of shading that can occur frequently would be shading for a collector or a window by nearby trees, buildings, or other obstruction. If they have a regular shape, if it's a building, then things are easy. But if it's a tree that's going to take a random shape, it's difficult to model it. So you'll have to look for what is the best or what is the closest geometry that can determine the tree so that you can be able to estimate how would it be. Sometimes the shading becomes as a problem that has been done in the installation. If you are using a large number of solar collectors, the large numbers are going to be placed in rows. The distance between the rows should be done accurately so that you can avoid one row is being shading the others. Definitely the first row will not be shaded, but the second row, third row or so might be shaded. And I'm going to share with you, I'm going to put like a file that has some internet links. And one of the links was somebody who's talking about this issue of the effect of shading of one row to the other and what we should do to make sure that there's no shading effect and it should not be overdone. For example, the distance that should be for a certain location on the earth between two rows of solar collectors is supposed to be 1.5 meters. Why should we do it 2 meters? That will be a waste of space. So the issue of accurately calculating it, not very accurately, but roughly, so that you do not overdo it in terms of the distances between the rows of collectors. The third one is shades by overhangs. And we talked about the overhangs when we were talking about the profile angle. If you remember, they said that sometimes you need to do that. Like if you need to protect your window from additional solar energy coming in because we're almost, the weather is warm most of the year. And having sun radiation coming through the window is going to require that we use a more effective or maybe a bigger air conditioner. So one way to resize or downsize the air condition is by having some sort of overhangs or shadowing effects you do for your windows. And if you are moving here in the streets, you can find that sometimes they are using decorative layer with very large surface which is covering uh, or making a shade on the building, especially if the building is made totally of glass. You can see that a lot in banks or so. You can find that they are putting sometimes outside of it some sort of a very big surface area with decorations, and the whole target is to make shadowing so that solar radiation will not penetrate through the glass, and then people are going to feel hot, whatever air conditioning that they are using. So that's going to be an easy matter if you are going to talk about regular shapes, but if the shapes are irregular, that becomes a problem. So we're just touching on the shading today, and this figure is one of the figures that show the solar position for a certain location over the year. The lowest line, the lowest curved line here is representing December, the winter solstice. The upper line up here is representing the summer. And in between, that's the rest of the year. And by the way, you have some sort of a symmetry here. If this line is supposed to be for December, then January following it, and then November, then October, March, September. So that's the way they are given. When you look at them, you'll find that they are pairs. Like for example, January and December are close to each other. February and October are close to each other. March and September are close to each other. April and August, and so on. So you'll find that the months are going to be paired, and they are paired going from the middle of the year and spreading in a similar way or in a symmetric way to the rest. For example, June and July, these are the middle. June is month number 6, July is number 7, so the lines are close to each other, and so on. And the hours of the day also, they are given the values here. The window that we are interested in basically is this window. They call it the solar window, where basically the sun is more effective from 9 o'clock in the morning up to 3 o'clock in the afternoon. So this is the solar window where you are going most of the radiation throughout the day. So whenever you have a figure like that, this is the location that you want to look for. What we do practically is that you take this, the figure that we have here, I think it was for Wisconsin-Madison, and each city is going to have a similar figure like that. You take this figure and you sit while you are facing south. This is south, and then you are going to west direction or east direction. You are facing south, and then you can overlay in your location what are the obstacles that you expect. What we have here is the azimuth angle, and this is the direction going from south to west and south to east. And what we have in the y-axis is basically the solar altitude and the zenith angle. Remember, there is a relation between the solar altitude angle and the zenith angle, that the summation of them is 90. So this is 90, this has to be 0. This is 80, this has to be 10. This is 20, this has to be 70, and so on. And then you can anticipate, based on the solar altitude, how long is the buildings that you have. And in the orientation you are standing in, you can determine whether the shading is going to affect your location or not. An example of that is being given here, where this thing has been laid for a city of San Francisco. You can see it here. You are sitting in a certain location, and your location here, you can like take a photograph and see what kind of obstructions that you have in front of you here. Scale these obstructions to the solar elevation, and then you can overlay it on this figure. Then you can notice here that you have a problem only in the first hour of the effective period from 9 to 10 in December and January and November. So during this period, you might have some sort of a shading in the first hour in the morning, so that you would know, but the rest are fine. So there's no shading problem with the rest, and that would be the right location to put your solar collectors. There is a website on the University of Oregon in the United States, where they make one software freely available. All you have to do is to put the latitude and the longitude of your city in addition to the time zone. For example, San Francisco has a latitude of 38, a longitude of minus 120 because it is the west of Greenwich line. And then the solar time zone, so the time there is Greenwich time minus 8 hours. And accordingly, this figure has been generated. I tried that last night. I went to that location or the site in Oregon State Universities to the website, and then I put the latitude, the longitude, and the time zone of Dhahran, who are here in the Saudi Arabia, basically is +3. So I put the latitude, I think 26.4, and the longitude, which is about 50. I put it there, and I got this figure to represent the solar motion. Actually, what I did not really adjust the figure. I should have adjusted it so that I would say I need the minimum or the x-axis to be just extended from 60 to 300, but I just did it for the whole spectrum. So that's something that we can adjust so that the figure would be having a better shape. And our sun window here is this one that extends from 9 o'clock in the morning here. Sorry, my hands are not moving exactly on the figure, but it's roughly, it is something like this, up to 3. So in Dhahran, this is our solar window, which is basically this. All of this is the solar window. So this is the time where the sun is actually producing us with effective radiation. What we do now, if I'm going to go in any location in Dhahran, I would stand and taking this paper in with me, and I would face south, and then accordingly I can look at the buildings that are around me here, and then I can plot these buildings in front of me and see if you have a very high-rise building, is it going to block part of it or not, and then we can, based on that, select the right location for putting your solar panels. Is that clear? Any question? So the rest of the part which is related to 1.9 shading, we are not going to cover in this chapter, but we'll cover it separately in a later chapter. So you may, if you want, while you are studying or trying to solve problems, examples, you are going to skip the 1.9 now, or just given an idea, rough idea about it, but we'll go back to it in a later stage in our course.
Doctor,
Yes.
how we could add the building height in this to this chart?
Yeah, what you do here is that you are going to see what is the height of the buildings that you have in front of you and estimate the angle at 9 o'clock, what is the angle that you have, and then see what would be the corresponding value as if you are overlaying it. Maybe we can think of an example and make it like a live example for you. Maybe I can work out an example and then share it with you later, so that you can see how the building heights can be overlaid on a figure like this. But you would estimate the building height with relation to the latitude angle or the solar elevation. So that 10 degrees are corresponding to how many meters height, 20 degrees are corresponding to how many meters height, and so on. And then you put it in here, and then you'll see if you have something covering your solar or anticipated solar collectors here or not.
Okay, thank you.
Yeah. Maybe it's, I can just quickly consider your attendance. I did not check it today. Maybe that's something that we can see. So, Abdul Hadi, Abu Zaid,
Yes.
Abdullah, Abu Shaya,
Yes, present.
Abdul Rahman, Al-Mashhaf,
Yes, present.
Yusuf, Muhaish,
موجود يا دكتور.
عمار الثملي.
Yes.
حسين الوحيد. صالح البيهي. صالح.
Yes, doctor.
Okay. عبد الله الدوسري. Okay. Then عمر الجهني.
Yes, doctor.
عبد العزيز المقثوي.
Yes, present.
عمر الشمري. Okay. عبد العزيز الشهري.
Yes, doctor.
ريان الودعي.
Yes, doctor.
فهد الزهراني. عبد الرحيم بيمة. عبد الرحيم. نواف الكعبي. نواف. أحمد خواج.
Yes.
أحمد سندي.
Yes, doctor.
and ياسر شايفل.
Yes, doctor.
Okay. Okay, so let's get back again to just I will just share again the file that we have, and this is where we were. Yeah. Now, in some or several of the radiation calculations, we would use normalized radiation level, so that the radiation level we try to compare it to the theoretical possible. And the theoretical possible would occur, as you know, if we don't have an atmosphere, which means that this is basically what comes from the sun up to the tip outside the atmosphere of the Earth. This is the maximum radiation, and the radiation reduces as the rays or as the waves are crossing the atmosphere because of several distracting elements like that result in diffuse radiation, definitely. Like, for example, talking about the clouds, talking about sand particles that are suspended in the air so that the reflect part of the energy of the radiation falling into them, or due to humidity, for example, where humidity can, water vapor can absorb part of the energy, or if you have like the carbon dioxide. Carbon dioxide is known to be a participating medium. Whenever you have carbon dioxide, it absorbs radiation, and probably you would know that this is one of the problems associated with global warming, because there is plenty of combustion processes occurring in factories, in cars, and so on. So there is a tremendous amount of carbon dioxide that's being emitted. Carbon dioxide is spreading in the air, and it absorbs radiation and then becomes a little bit hot. And then it heats the air around it. And that's what's responsible for the problem of global warming. So the highest radiation is the extraterrestrial radiation, which is outside the atmosphere. What we need to do now is, at any point of time, the solar radiation incident on a horizontal plane outside the atmosphere is the normal incident solar radiation as given by equation 141 that we have taken earlier to determine the value of GON divided by RB. Accordingly, this extraterrestrial radiation is given as the solar constant multiplied by this fraction, which is 1 plus 0.033 cosine 360 n over 365. We have taken this equation earlier in just to determine how much is the radiation falling with respect to the solar constant, and then multiplied by cosine theta z. And n definitely is representation of the day of the year. Now, if we need to substitute for the value of cosine theta z, which is cosine zenith angle, by the expression that we took for it, then we can represent it here as cosine phi, cosine delta, cosine omega plus sine phi, sine delta. Accordingly, we may use this expression here for estimation of the daily solar radiation. And we can even calculate it by instant solar radiation, or some sort of a solar radiation which is monthly occurring on the surface. Do we need this? The answer is yes, because sometimes when you are putting a solar collector, you would not be calculating how much is the energy every hour. You might globally, because you need to estimate, for example, or comparing between a couple of collectors that are going to be used to take a certain load. Let me give an example. In one of the years, maybe in 2015, we started a project. This project was done for what is called at that time the Ministry of Water and Electricity. It has changed, the name has changed. This was basically, we were looking for the potential of having solar collectors for water heating in the domestic sector. By the domestic sector, we mean hotels and hospitals. So we needed to take some samples of hotels and hospitals in different places in the kingdom to represent different climatic zones and see how much is the load that they need for heating the water. So that was basically dependent on how much water they are using. So for a hotel, what is the average occupation rate? And accordingly, how much water is going to be consumed roughly by a person, how much water they need for the laundry, for cleaning, and so on. And we estimate in general how much is the total consumption of water. Out of this water in winter seasons, how much do they need water heated? Definitely, winter season is going to be higher than the summer season, but there are some applications that will not be affected by the season where you need hot water. Talking about laundries, for example. For a laundry, you need hot water always. So either you have a heater built in your laundry, which is not quite often occur, or you just bring hot water to it, to the machine, to the washing machine. So the point here is that we're calculating how much is the load which is being required to be covered for every month of the year. We cannot do it for every day because this is tedious to do. And it's not worth, because the accuracy that we are going to get on a monthly basis is going to be good enough. Then we can determine on a monthly basis what is the average Q or heat transfer needed to be transferred to the water to be heated. This heat transfer, or this Q, should be supplied by solar collectors. So accordingly, our calculations were based on a monthly average value of Q that is going to be provided by the solar collectors. So the issue of talking about an hourly base or a daily base or a monthly base, it has its own applications. And that's something which is needed. One example is what I mentioned to you. We did that for hotels, we did that for hospitals as well. And again, for hospitals, they need continuous supply of hot water for the operations. They need it for, again, the laundry. So several applications they would do. And these institutions, whether they are hotels and hospitals, are using either electric heaters, which is resulting in consumption of tremendous amount of or tremendous rate of energy consumption by electric heaters, and many of them are using boilers, and the boilers are being operated by fossil fuel, basically diesel, and this actually results in emissions of CO2. So our study was basically to look at the feasibility of using solar energy, and the feasibility here is number one, technical, Number two, economical. They are going to buy solar collectors. So what is the payback period after how many years? And the third part was environmental. How much or how many tons of carbon dioxide are we saving by stopping the use of conventional energy, be it diesel or electricity? For electricity, there are some power plants somewhere that are burning fuel to generate electricity. So that also results in a contribution to the global warming and the emissions to the surroundings in terms of CO2. So the study was based on that. And basically, what we were looking for was the monthly consumption by calculating Q over a month. So it is often necessary to calculate the solar radiation on a daily basis or on even a monthly basis. And the daily basis is integration of the instantaneous radiation over the day. Monthly basis is integration over the month. You can do it even for an hour or a couple of hours by integrating it for a period of time. So integration of the equation or the equation that we have here, equation 110.2, which is the first equation in the slide that you see in front of you, that needs to be integrated over the day. What is changing here over the day? The value of omega changing. So you are going to integrate it with respect to omega. If you are talking about for how many hours, it's a limited integral from sunrise to sunset. When you do that, you are going to get the equation down there. So we have changed the expression from G, which is in terms of watts, joule per second, to H, because we have integrated over the time, and this is given in joules per square meter. You can see here the values of the integration has been calculated, and the integral expression of H naught is being given here. So this is, you can consider it as some sort of H given per square meter on a daily basis, because we did the integration here from we don't do the integration for the 24 hours because the sun is not there in the 24 hours, but you are going to do it basically from sunrise to sunset. And this equation is a representation of that, where the WS that we have here basically is the sunset hour, and that tells that we have integrated omega up to the sunset. And then we may need also to get a monthly mean. And the monthly mean, we are going to use H naught bar. The bar here is meaning that we are talking about the value for a whole month. So the G naught is an instantaneous value depending on the hour of the day. H is an integration or H naught integration all over the day. H bar or H naught bar is the integrated value for the whole month. And these values are given in terms of equation, as you can see it here. They are also given in terms of a table, or even given as a chart. And there are charts that are given these values. And that's something that you can see here. Here you can get the value of H naught, the monthly mean value based on the latitude and the time of the year that you have. For example, these are 12 lines. Each line is representing a certain month. June 11, July 17, May 15. And if you need somewhere in between, again, you're going to like visually interpolate. Like I'm looking for August 30. The 30th of August, maybe I can come up with something here for the instantaneous value. But as long as the month is concerned, every one of them is representing a month. So what is the latitude of your city? In our case, we are talking about Dhahran is 26.4, so we are somewhere here. You're going to move up and get the monthly radiation in terms of energy for this month of the year. Figures are making life easy, but accuracy is the penalty, is the drawback for this. And the daily one is being given here as well. That's for the south latitude. So this one for the north latitude, and this one is for the south latitude. And the values are given as megajoule per meter square. Then you can calculate for a certain day, for example, what is the solar radiation that are falling in. This also is not only given in terms of a chart or a figure, but it's also given here in terms of a table. So here, based on the latitude, whether you are in the northern part of the hemisphere or the Earth, or a southern hemisphere, southern part of the Earth, you can get the values of H bar naught from here, megajoule per meter square. So for example, you are talking about a latitude of 30. For a 30 latitude in March, the value is 31.5. What if you are talking about somewhere between 40 and 45? Then we have to interpolate. If it's like 42, then you do an interpolation between these 2 points to get what is the point in the middle, and so on. So using a figure or using a chart is going to make our life easier, although we still have the option of using the equation to get more accurate results. But the point here, practically speaking, somebody in the field, they need something that they call back of the envelope calculation, something that you can do quickly and get a result which is not necessarily 100% accurate, but it's something that you can live with their accepted accuracy. Then figures are a very, very good choice for that. The example that was mentioned in one of the videos is talking about engineers. Probably I can use that to conclude our talk today. And we are going to talk about this example. We have a couple of examples on this. We can start with this example on our next class, inshallah. But they are talking about engineers who are used the micrometer to measure. And then they use an axe, fas, for cutting, which means that all that you have done earlier for very accurate estimations, it can be affected by the way that you are putting your units. For example, I can have a compass where I can determine exactly what is the south direction. But when I put my sonar collectors, I can put them tilted a few angles here, like here or there, and go in the azimuth direction, which is expected, so that you might be doing very accurate results, but when you're applying it on the ground, then you might be relaxing some of this accuracy just for the case, or for the sake of putting some sort of an easy installation or so. So now we're talking about equations that are there for calculating the energy flux, which is falling on the ground as watts per meter square, joules per meter square, or you can use figures that can be used for this determination, or you can use charts, figures or charts, or you can use tables to do that. And what we'll be starting with in our next class, start with a couple of examples where we can do the same thing. We can use an equation, we can use the chart, and then we can use the table just to estimate the values, for example, the value of H naught for a certain latitude and on a certain day of the year. So we'll be using basically the equation, we'll be using the chart, and we'll be using the table to obtain that. That would be it for today. I'm concluding, and then we are going to finish these 2 examples in our next class, inshallah, and then start in the next chapter. I have to tell you that homework set number 1 is ready. It will be released in the Blackboard at 10 o'clock today. And it's about 5 problems that are a direct substitution to the all the elements that we have covered in this chapter. It is due on January 7, which is something like 11 days from now or so, inshallah. Monday, sorry. Not next week, but the week after, inshallah. Questions or comments?
Thank you, Doctor.
Okay,
Thank you.
thank you. So we'll see you next time, inshallah, on Monday.
Inshallah.
See you.
يعطيك العافية دكتور.
الله يعافيك، شكرا لك.